In the vast darkness of space, far beyond anything the human eye can perceive, there exist objects so dense, so massive, so utterly profound in their gravitational pull that they reshape the very fabric of the universe around them. These are the supermassive black holes, the gentle giants that rest at the hearts of galaxies, silent architects of cosmic structure, patient gardeners of starlight, waiting in the endless night with a gravity so deep that not even light itself can escape their embrace. And tonight, as you rest, as your breathing slows and deepens, we'll drift together through the quiet cosmos, exploring these magnificent mysteries that dwell in the centers of island universes, these places where time itself bends and stretches like warm honey, where the laws of physics dance at the edge of comprehension, where matter spirals inward in a slow, eternal waltz that is continued for billions upon billions of years. Imagine, if you will, a single point in space, so small it has no dimensions, yet containing the mass of millions or even billions of suns, all compressed into a region smaller than our solar system, sometimes smaller than the orbit of Mercury. A pinpoint of such incredible density that the mind cannot truly grasp it, only marvel at it softly, gently, as one might marvel at the stars on a clear summer night. This is the heart of a supermassive black hole, the singularity, a place where all our normal rules break down, where equations fail and intuition abandons us, leaving only the quiet certainty that something profound and strange exists there, hidden forever behind an invisible boundary called the event horizon, that gentle threshold beyond which nothing returns, not matter, not energy, not information, not even the photons of light that race through space at 300,000 kilometers per second, for even they are too slow to escape once they cross that peaceful, fatal line. The event horizon is not a physical surface, not a wall or a barrier you could touch, but rather a mathematical boundary, a point of no return defined purely by gravity, by the curvature of spacetime itself, and if you could somehow approach one, you would see nothing unusual at first, just the black of space growing darker, the stars behind you beginning to shift in color and position as the intense gravity bends their light around you, distorting your view of the universe like looking through a lens that grows stronger and stranger with every kilometer you fall. And you would be falling, always falling, for near a black hole there is no standing still, no hovering in place, only the inexorable pull downward, inward, toward that hidden center where the singularity waits in patient darkness. Supermassive black holes are found at the centers of nearly every large galaxy in the observable universe, quiet companions to hundreds of billions of stars, anchors around which entire galactic communities orbit in their slow, stately dance through the eons. Our own galaxy, the Milky Way, that river of light that arches across dark skies on moonless nights, harbors such an object at its heart, a supermassive black hole called Sagittarius A star, resting some 26,000 light-years from Earth, sitting quietly in the constellation Sagittarius, weighing in at approximately 4 million times the mass of our Sun, yet occupying a space only slightly larger than the orbit of Mercury, that small, swift planet that races around our Sun every 88 days. 4 million suns, compressed into such a relatively tiny volume, creating a gravitational well so deep that stars near it move at incredible speeds, some reaching velocities of thousands of kilometers per second as they whip around this invisible anchor in elliptical paths that carry them close, so close to the event horizon before flinging them back out into the relative safety of the wider galaxy. We know Sagittarius A star is there not because we can see it directly, for black holes emit no light of their own, being by definition the absence of light, the negation of visibility, but because we can see its effects on everything around it. Astronomers have patiently watched stars near the galactic center for decades now, tracking their motions year after year, plotting their orbits with painstaking precision, and what they've found is remarkable, beautiful in its implications, for these stars move not in random paths, but in perfect ellipses around a point, an empty point in space that must contain an enormous mass, something millions of times heavier than the Sun, yet completely invisible. And the only thing that can be, the only object that fits all the observations, is a supermassive black hole, sitting there in the darkness, pulling on everything nearby with its immense gravity, but never revealing itself directly. The story of how supermassive black holes form is one written in the very early universe, in that ancient time just a few 100 million years after the Big Bang, when the first stars were being born, when galaxies were just beginning to coalesce from the vast clouds of hydrogen and helium that filled all of space. In that epoch, now so distant that its light has taken most of the age of the universe to reach us, conditions were different. The universe was smaller, denser, hotter, and in that environment, the first black holes began to form. Some grew from the deaths of massive stars, those giants that burned through their nuclear fuel in mere millions of years before collapsing catastrophically, their cores imploding to form stellar mass black holes weighing perhaps 10 or 20 or 50 times the mass of the Sun. But these were just the seeds, the beginnings of something much larger, for in the dense environments of the early universe, these black holes found themselves surrounded by abundant gas, endless clouds of pristine hydrogen waiting to be consumed, and so they fed, slowly, steadily, growing more massive with each passing million years. As these early black holes grew, they pulled in more and more material, their event horizons expanding, their gravitational reach extending farther into space, and some of them found themselves at the centers of the first proto-galaxies, those clumps of matter that would eventually grow into the grand spirals and ellipticals we see today. There, at the gravitational centers of these forming galaxies, the black holes had access to enormous amounts of gas, and they grew rapidly. Relatively speaking, though even rapidly in cosmic terms means millions and millions of years, timescales so vast that human civilization could rise and fall countless times in the span of their growth spurts. And so, over billions of years, these seed black holes became the supermassive monsters we observe today, objects weighing millions or billions of solar masses shaped by gravity and time into the most extreme objects in the universe. But not all supermassive black holes grow steadily and quietly. Some go through periods of intense activity, times when vast amounts of gas and dust fall toward them, forming what astronomers call an accretion disk, a swirling, rotating disk of material that orbits the black hole, spiraling slowly inward like water circling a drain, though this process happens over thousands or millions of years rather than seconds. As matter in the accretion disk falls closer to the event horizon, it accelerates, reaching speeds that are significant fractions of the speed of light, and this motion generates friction, heating the material to millions of degrees, so hot that it glows brilliantly in X-rays and ultraviolet light, transforming the area around the black hole into one of the brightest objects in the universe. These are called active galactic nuclei, or quasars when they're especially luminous, and they can outshine their entire host galaxies, billions of stars rendered invisible by the blazing light of material falling into a single supermassive black hole at the galactic center. Quasars were more common in the early universe, back when galaxies were younger and richer in gas, when supermassive black holes were still growing rapidly, still feeding hungrily on the abundant matter around them. Today, most supermassive black holes, including our own Sagittarius A star, are relatively quiet, dormant, with only small amounts of material trickling into them, producing only faint emissions that require sensitive instruments to detect. But they still exert their influence, their gravity shaping the orbits of stars across the galactic center, their presence affecting the evolution of the entire galaxy. And occasionally they'll encounter a fresh supply of gas, perhaps from a wandering star that passes too close, or from two galaxies merging and funneling gas inward, and then, for a time, they'll flare to life again, blazing with renewed intensity before settling back into quietude. The relationship between supermassive black holes and their host galaxies is intimate, subtle, a cosmic partnership that has puzzled and delighted astronomers for years. Observations have revealed that the mass of a galaxy's central supermassive black hole is closely related to the properties of the galaxy's bulge, that central concentration of stars that exists in most large galaxies. Specifically, the black hole's mass is typically about 1,000th the mass of the bulge, a relationship so consistent that it suggests something fundamental, some deep connection between the growth of supermassive black holes and the formation of galaxies themselves. This is remarkable when you consider the scales involved. For the black hole, even a supermassive one, occupies only a tiny fraction of the galaxy's volume. Yet somehow its growth is synchronized with the assembly of billions of stars across thousands of light years. The explanation, astronomers believe, lies in feedback, in the energy that active black holes pump back into their surroundings. When a supermassive black hole is actively feeding, consuming large amounts of gas, it doesn't just glow brightly. It also generates powerful winds and jets, streams of particles accelerated to nearly the speed of light that shoot out from the vicinity of the black hole, perpendicular to the accretion disk, extending for thousands or even millions of light years into intergalactic space. These jets carry tremendous amounts of energy, and as they plow through the surrounding gas, they heat it, pushing it away, preventing it from cooling and condensing into new stars. In this way, an active supermassive black hole can regulate star formation across its entire galaxy, turning off the process of stellar birth when it feeds too vigorously, allowing the galaxy to develop in step with the black hole's own growth. It's a delicate balance, a cosmic thermostat that has shaped the evolution of galaxies across billions of years. The jets themselves are wonders worth contemplating as you drift toward sleep. These narrow beams of particles and energy can extend for incredible distances, far beyond the visible galaxy, out into the dark spaces between galaxies, creating enormous structures called radio lobes, vast bubbles of energized particles that glow in radio wavelengths, some of them spanning millions of light years from end to end, dwarfing the galaxy that spawned them. The jets are powered by a combination of the black hole's gravity and its rotation, with the intense magnetic fields around the black hole somehow twisting and focusing material into these narrow beams, accelerating particles to enormous speeds, creating what is essentially the largest particle accelerator in nature, far surpassing anything we could ever build on Earth. And these jets are stable, coherent, remaining focused over distances that light itself takes millions of years to cross, a testament to the organizing power of magnetic fields and the persistent rotation of the supermassive black hole at their base. Time behaves strangely near a supermassive black hole, stretched and distorted by the intense gravity, flowing at different rates depending on how close you are to the event horizon. This is a consequence of Einstein's general relativity, that beautiful theory that describes gravity not as a force, but as a curvature of spacetime itself, the four-dimensional fabric that combines the three dimensions of space with the single dimension of time into one unified whole. Near a massive object, spacetime curves, bends inward like a depression in a stretched rubber sheet, and clocks tick more slowly, time itself dilating, stretching out compared to time measured far away from the source of gravity. Near a supermassive black hole, this effect is extreme, and if you could watch someone fall toward the event horizon from a safe distance, you would see them slow down, their movements becoming more and more sluggish as they approached that boundary, until finally they appeared to freeze, suspended forever at the event horizon, never quite crossing it, at least not from your perspective. Though from their own point of view, they would cross it in finite time, experiencing nothing unusual at the moment of crossing, only the continued fall toward the singularity within. This strange behavior of time creates what astronomers call gravitational time dilation, and it has been measured, confirmed through experiments with atomic clocks at different altitudes on Earth, where gravity is stronger at sea level and weaker at high altitude, causing clocks to tick at measurably different rates. Near a supermassive black hole, this effect would be magnified tremendously, so that if you could somehow position yourself just outside the event horizon and remain there for what felt like an hour to you, many years might pass in the universe beyond, the galaxy spinning faster, stars being born and dying, civilizations rising and falling, all while you experience just 60 minutes of time, protected from aging by the intense curvature of space-time around you, though protected is perhaps the wrong word. For the tidal forces, the difference in gravitational pull between your head and your feet would be catastrophic at such proximity to the event horizon, stretching you like taffy in a process astronomers cheerfully call spaghettification. The structure of a supermassive black hole is both simple and profoundly complex. At the center lies the singularity, that point of infinite density where all the mass is concentrated, though calling it a point is perhaps misleading. For our understanding of physics breaks down there, quantum effects that we don't yet know how to calculate becoming important. And it may be that the singularity is not a point at all, but something else entirely. Some strange quantum structure that we lack the mathematics to describe. Surrounding the singularity is the event horizon, that boundary of no return, a sphere whose radius depends on the mass of the black hole, growing larger as the black hole accumulates more material. For a supermassive black hole of 1 billion solar masses, the event horizon would be about 3 billion kilometers across, roughly the size of Neptune's orbit around our Sun. A vast region of space from which nothing emerges, inside of which spacetime is so severely curved that all paths lead inward toward the singularity, regardless of how fast you try to move or in what direction. But there's more to the structure than just the singularity and the event horizon. Some black holes, perhaps most or even all, are rotating, spinning around an axis like a top, and this rotation drags spacetime around with it, creating a region called the ergosphere, a zone outside the event horizon where the rotation of the black hole is so powerful that nothing can remain stationary. Everything is forced to rotate in the same direction as the black hole, though it's still possible to escape from the ergosphere, unlike from within the event horizon. This rotation also affects the shape of the event horizon, flattening it at the poles and bulging at the equator, creating an oblate spheroid rather than a perfect sphere. And the faster the rotation, the more pronounced this distortion becomes. At the maximum possible rotation rate, the event horizon would be spinning at the speed of light at its equator, a limit set by the laws of physics, though we don't know how common such rapidly rotating black holes are in nature. The matter that surrounds an active supermassive black hole, the material in the accretion disk, exists in a plasma state, so hot that electrons are stripped from atoms, creating a soup of charged particles that interact strongly with magnetic fields. These fields are generated by the motion of the plasma itself, twisted and amplified by differential rotation, where the inner parts of the disk orbit faster than the outer parts, creating a dynamo effect that can produce incredibly powerful magnetic fields so strong they can affect the motion of the plasma, channeling it, guiding it, sometimes launching it outward in those relativistic jets we discussed earlier. The physics of these accretion disks is complex, involving magnetohydrodynamics, a branch of physics that combines the study of magnetic fields with fluid dynamics, and despite decades of theoretical work and computer simulations, there's still much we don't understand about how exactly these systems work, how they transport angular momentum, how they generate their magnetic fields, how they launch their jets. As material in the accretion disk spirals inward, it must shed angular momentum, that property of rotating objects that quantifies their spin, and this happens through viscosity, through friction between adjacent layers of the disk, though the exact mechanism of this viscosity is still debated. The inner edge of the accretion disk typically extends down to the innermost stable, circular orbit, a location that depends on the black hole's rotation, but is roughly 3 times the Schwarzschild radius. That is, about 3 times the radius of the event horizon for a non-rotating black hole. Inside this radius, there are no stable orbits. Particles cannot circle the black hole indefinitely, but instead plunge rapidly inward, crossing the event horizon in a fraction of a second, disappearing from our universe forever. This innermost stable orbit is where the accretion disk ends, where the hot glowing plasma makes its final dance before vanishing into the black hole, and observations of X-ray emissions from this region have provided some of our best evidence for the existence of event horizons, where the signatures of the innermost stable orbit appear in the X-ray spectra, imprinted by the extreme environment just outside the point of no return. Supermassive black holes grow through 2 primary mechanisms, through the accretion of gas and dust from their surroundings, and through mergers with other black holes. The first process, accretion, is relatively steady and continuous, at least on cosmic timescales, though it can vary dramatically over shorter periods as the supply of inflowing material changes. When a supermassive black hole accretes matter efficiently, it can grow quite rapidly, doubling its mass every few tens of millions of years. Though this requires a sustained supply of gas, something that becomes less common as galaxies age and use up their reserves of pristine hydrogen. The second process, mergers, occurs when two galaxies collide and combine, bringing their central supermassive black holes into proximity, where they eventually sink to the center of the merged galaxy through a process called dynamical friction, gradually spiraling together over millions of years until finally they merge in a catastrophic collision that releases enormous amounts of energy in the form of gravitational waves, ripples in spacetime itself that propagate outward at the speed of light, carrying information about this violent union to distant observers. Gravitational waves from supermassive black hole mergers are different from those we've detected so far with instruments like LIGO and Virgo, which observe mergers of stellar mass black holes weighing tens of solar masses. The waves from supermassive black holes have much longer wavelengths, periods measured in years rather than fractions of a second, and detecting them requires different techniques, specifically using arrays of pulsars, those rapidly rotating neutron stars that emit regular pulses of radio waves with the precision of atomic clocks. By carefully timing the arrival of pulses from many pulsars scattered across the sky and looking for correlated variations in those arrival times, astronomers can detect the passage of gravitational waves from supermassive black hole mergers occurring across the universe. This technique, called pulsar timing arrays, is just beginning to show results with recent hints of a gravitational wave background, a sort of cosmic hum produced by many such mergers occurring throughout the universe at different times and distances, their waves overlapping and interfering to create a complex signal that permeates all of space. The environment immediately surrounding a supermassive black hole is one of the most extreme in the universe, a place where gravity is intense, where radiation is fierce, where magnetic fields are powerful enough to accelerate particles to nearly the speed of light. And yet, remarkably, it's also a place where we find structure, where disks form and jets emerge, where there's order amid the chaos. This order emerges from the interplay of physical processes, from the balance between gravity pulling inward and pressure pushing outward, from the conservation of angular momentum requiring material to spread into a disk rather than falling directly inward, from the tangled dance of magnetic fields threading through plasma, organizing it, channeling it, sometimes launching it into space at relativistic speeds. In studying these extreme environments, we learn about physics in regimes we can never recreate in laboratories on Earth, where gravity is billions of times stronger than anything we can produce, where particles move at speeds that make our most powerful accelerators look sluggish, where spacetime itself is bent and twisted into shapes that challenge our intuition and our mathematics. The observation of supermassive black holes has advanced remarkably in recent decades, driven by improvements in telescope technology and techniques. Radio telescopes linked together across entire continents or even across the globe can achieve angular resolutions fine enough to see the regions immediately around supermassive black holes in nearby galaxies, resolving structures just a few times larger than the event horizon itself. This technique, called Very Long Baseline Interferometry, or VLBI, combines signals from many radio dishes to create a virtual telescope as large as the distance between them, and in recent years, this has culminated in the Event Horizon Telescope, a planet-wide array that captured the first direct image of the region around a supermassive black hole, specifically the one at the center of the galaxy Messier 87, a giant elliptical galaxy about 55 million light-years away in the constellation Virgo. That image, released in 2019, showed a bright ring of emission surrounding a dark central region, the shadow of the black hole, where the intense gravity bends light rays from the accretion disk, creating a silhouette roughly 2.5 times the size of the event horizon. The ring appears brighter on one side than the other, an effect of the rotation of the disk, where material on one side is moving toward us and therefore appears brighter due to relativistic beaming, while material on the other side is moving away and appears dimmer. This asymmetry tells us about the rotation of the accretion disk, which side is approaching and which is receding, and measurements of the size of the shadow confirm the mass of the black hole, about 6.5 billion solar masses, consistent with estimates made through other methods. The achievement of capturing this image required the coordination of 8 radio observatories around the world, from Hawaii to Chile to Antarctica, all observing the same target simultaneously, recording petabytes of data that was later correlated and combined to produce the final image, a technical tour de force that demonstrated what's possible when science is truly global and collaborative. Since that first image, the Event Horizon Telescope has continued its observations, capturing images of Sagittarius A star, our own galactic center, though this proved more challenging, because the smaller mass of that black hole means the accretion disk changes on timescales of minutes rather than days, like watching a dynamic, flickering flame rather than a steadier glow. But the images have been obtained and analyzed, revealing a similar ring structure, confirming that Sagittarius A star is indeed a supermassive black hole and providing measurements of its properties with unprecedented precision. These observations mark the beginning of a new era in black hole astronomy, where we can not just infer the presence of these objects from their effects on surrounding matter, but actually see the signatures of the event horizon itself, observing the shadow where light cannot escape, peering at the very edge of the observable universe, not in distance, but in space-time curvature. The interior of a black hole beyond the event horizon is a place of endless fascination and speculation, for it's a region forever hidden from outside observers, sealed off by the one-way nature of the event horizon. Once inside, the roles of space and time undergo a strange reversal, or at least, that's one way to think about it, where moving forward in time necessarily means moving inward toward the singularity, just as surely as we move forward in time in our everyday lives. In this sense, the singularity becomes not a place but an event, a moment in the future for anyone who crosses the event horizon, unavoidable as tomorrow. The journey from the event horizon to the singularity takes time, at least from the perspective of someone making that journey, and for a supermassive black hole, this time could be hours or even days, unlike for a stellar mass black hole where it would be just fractions of a second. During that time, the infalling observer would experience tidal forces growing stronger, stretching them along the radial direction while compressing them in the perpendicular directions, those forces eventually becoming infinite at the singularity itself, though likely becoming fatal long before that, tearing apart first the body, then molecules, then atoms, then perhaps even atomic nuclei, reducing everything to a stream of elementary particles. But what happens at the singularity itself? This is where our current theories fail us, where general relativity predicts infinite curvature and infinite density, quantities that signal not a true feature of nature, but rather the breakdown of the theory, a sign that we need a quantum theory of gravity to describe what really happens there. Such a theory doesn't yet exist, at least not in complete form, though there are candidates, string theory and loop quantum gravity being the most developed, both suggesting that the singularity might be resolved into some kind of quantum structure, perhaps a region of extremely high but finite curvature, or perhaps something even stranger, a connection to another universe, a remnant of quantum foam, or a structure we don't yet have the concepts to describe. Until we have a complete theory of quantum gravity, tested and confirmed through observation, the singularity remains a mystery, a place where our equations give up and we're left with only speculation and mathematics that hints at possibilities without confirming them. There's also the question of what happens to information that falls into a black hole, a puzzle that has occupied theoretical physicists for decades. According to quantum mechanics, information cannot be destroyed, it can only be transformed or dispersed, yet a black hole appears to destroy information, swallowing it beyond the event horizon where it can never be retrieved. This apparent contradiction, known as the black hole information paradox, has led to proposals that information might somehow be preserved, perhaps encoded on the event horizon itself in what's called the holographic principle, or perhaps gradually released through Hawking radiation, that quantum process by which black holes can slowly evaporate over immense timescales. Stephen Hawking showed in the 1970s that quantum effects near the event horizon can create pairs of particles, one of which falls into the black hole while the other escapes, carrying energy away, causing the black hole to slowly lose mass, to radiate as if it were a warm body with a temperature inversely proportional to its mass. For supermassive black holes, this temperature is incredibly low, far below the temperature of the cosmic microwave background, meaning they're currently absorbing more radiation than they emit, growing rather than shrinking. But in the far future, after the universe has expanded and cooled for trillions upon trillions of years, even supermassive black holes will begin to evaporate, taking longer than the current age of the universe multiplied by billions of billions, to finally disappear in a last quantum gasp. The cosmic significance of supermassive black holes extends far beyond their immediate surroundings, for they've played a crucial role in shaping the large-scale structure of the universe. In the early universe, the first supermassive black holes helped regulate the formation of the first galaxies, their energy output preventing gas from cooling and collapsing too rapidly, allowing galaxies to grow in a controlled fashion over hundreds of millions of years. Later, as galaxies assembled into larger structures, groups and clusters containing dozens or hundreds of galaxies, the supermassive black holes at their centers continued to inject energy into the surrounding intergalactic medium, heating it and preventing it from forming new stars, helping to explain why the most massive galaxies in the universe, those found at the centers of galaxy clusters, are typically ellipticals rather than spirals, having exhausted their star-forming gas long ago under the influence of their central black holes and the hot cluster environment. In this way, supermassive black holes have acted as cosmic thermostats, preventing the universe from converting all its gas into stars too quickly, maintaining a balance that has allowed galaxies to evolve over billions of years rather than consuming all their fuel in the first few billion years after the Big Bang. The distribution of supermassive black holes across the universe also tells us about cosmic history, about how structure formed and evolved. Quasars, those extremely luminous active galactic nuclei powered by rapidly feeding supermassive black holes, were most common when the universe was between 1 and 3 billion years old, a cosmic epoch that corresponds to a time of rapid galaxy growth and merger activity when gas was still abundant and galaxies were frequently colliding, funneling material into their central black holes. Today, quasars are rare, most supermassive black holes having settled into dormancy, only occasionally flaring when a fresh supply of gas becomes available. By studying the population of quasars at different epochs, by measuring how their numbers and luminosities change with cosmic time, astronomers can reconstruct the feeding history of supermassive black holes across billions of years, learning when they grew most rapidly, when they were most active, how their activity correlated with the formation of stars in their host galaxies. This cosmic archaeology, reading the history of the universe from the light of distant objects, is one of the great achievements of modern astronomy, allowing us to piece together the story of how the universe evolved from the nearly uniform conditions of the early cosmos to the rich tapestry of structure we see today. Some supermassive black holes have been found at surprisingly early times, existing when the universe was less than 1 billion years old, and these pose something of a puzzle, for the standard growth mechanisms we've discussed, accretion and mergers, seem insufficient to grow black holes to billions of solar masses in the time available. These discoveries have prompted theorists to consider alternative formation scenarios, perhaps involving the direct collapse of massive gas clouds in the early universe, bypassing the stellar evolution stage entirely and forming black holes of thousands or even tens of thousands of solar masses from the start, giving them a head start on growth. Or perhaps these early supermassive black holes formed through the mergers of many smaller black holes in the dense environments of the first proto-galaxies. or perhaps they accreted gas at rates exceeding what we normally consider possible, somehow overcoming the radiation pressure that typically limits how fast a black hole can grow. The observations of these early monsters continue to challenge our understanding, pushing us to refine our theories and consider possibilities we might not have thought of otherwise. The relationship between supermassive black holes and dark matter is another area of active research. Dark matter, that mysterious substance that makes up about 85% of the matter in the universe, yet doesn't emit, absorb, or reflect light, forms vast halos around galaxies, providing the gravitational scaffolding upon which ordinary matter collects and forms stars. Supermassive black holes sit at the centers of these dark matter halos, and there's evidence that the properties of the halo, its mass and concentration, correlate with the mass of the central black hole, suggesting some connection between the two, though the nature of this connection is still unclear. Dark matter doesn't interact electromagnetically, so it can't form accretion disks or emit radiation, but it does interact gravitationally. And it's possible that dark matter particles are slowly captured by supermassive black holes, adding to their mass over cosmic timescales, though the rate of this process is likely very slow, much slower than accretion of ordinary matter. Still, in the far future, after all the ordinary matter has been consumed or ejected, dark matter accretion might become the dominant mode of black hole growth, slowly and steadily adding mass over trillions of years. There's also the intriguing possibility that black holes themselves might be made partly or entirely of dark matter, or that some dark matter might exist in the form of primordial black holes, objects that formed not from stellar collapse, but from density fluctuations in the very early universe, in the first second after the Big Bang. These primordial black holes could range in mass from tiny microscopic objects weighing less than a gram, to massive ones comparable to stellar mass black holes or even larger. And if they exist in sufficient numbers, they could account for some or all of the dark matter in the universe. Observations have constrained these possibilities, ruling out primordial black holes as the dominant form of dark matter across most mass ranges, but there remain certain windows where they could still contribute significantly, and the search continues through gravitational lensing surveys, looking for the telltale signs of compact massive objects passing in front of distant stars and, briefly, magnifying their light. The future of supermassive black holes, on timescales vastly longer than the current age of the universe, is a story of slow decline and eventual evaporation. In the near term, cosmically speaking, over the next few trillion years, galaxies will continue to merge, bringing their central supermassive black holes together, creating even more massive black holes at the centers of ever larger galaxies. Star formation will gradually decline as the universe uses up its reserves of hydrogen gas, and active galactic nuclei will become increasingly rare as the fuel for accretion runs out. Eventually, after 10 or perhaps 100 trillion years, the last stars will die, the last red dwarfs cooling into black dwarfs, and the universe will enter the so-called degenerate era, where stellar remnants, white dwarfs, neutron stars, and black holes are the only significant objects, drifting through the expanding darkness. Even these objects aren't eternal, for over timescales of 10 to the 35 years or longer, atomic nuclei can undergo proton decay if current theories are correct, causing even white dwarfs and neutron stars to slowly evaporate, leaving only black holes, which themselves will evaporate through Hawking radiation over timescales that depend on their mass. A supermassive black hole of 1 billion solar masses will take approximately 10 to the 98 years to evaporate, a number so large it's almost meaningless, a 1 followed by 98 zeros, longer than the current age of the universe by a factor larger than a billion trillion 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 trillion. During this vast span of time, the black hole will slowly radiate away its mass, growing hotter as it shrinks, following the inverse relationship between temperature and mass that characterizes Hawking radiation, until in the final moments of its existence, it will evaporate in a burst of high-energy particles, its last bit of mass converting to energy in accordance with Einstein's famous equation. What remains after this final evaporation is uncertain. Perhaps nothing at all. Perhaps some residual quantum state. Perhaps a stable remnant, the ultimate fate being one of those questions that will require a complete theory of quantum gravity to answer definitively. But the timescales involved are so enormous that they dwarf not just human experience, but the entire history of stars and galaxies, reminding us that the universe has many more chapters to come, far more than have already been written. In contemplating supermassive black holes, we're forced to grapple with concepts that push the boundaries of human understanding, ideas like curved spacetime, event horizons, singularities, concepts that seem almost mystical in their strangeness, yet are grounded in mathematics and confirmed by observation. These objects represent extremes, places where the universe shows us what's possible, where matter and energy behave in ways utterly unlike anything in our everyday experience, where time dilates and space curves and the normal rules seem to break down or transform into something new. And yet they're natural, inevitable consequences of gravity, of general relativity, of the tendency of matter to clump and concentrate under its own gravitational attraction. In a universe with gravity, in a universe where general relativity holds, black holes are not just possible but necessary, guaranteed to form whenever enough matter concentrates in a small enough volume, and supermassive black holes are the grandest expression of this tendency, the result of billions of years of matter falling, accumulating, concentrating at the gravitational centers of galaxies. The study of supermassive black holes connects many branches of astronomy and physics, from the observations of stellar orbits and accretion disks to the theory of general relativity and quantum mechanics, to the large-scale structure of the universe and the evolution of galaxies over cosmic time. They're nexuses where different fields meet and inform each other, where observations constrain theory and theory predicts new phenomena to be observed, where each advance in understanding opens new questions and new avenues for exploration. And they capture the imagination in a way that few other astronomical objects do, for they're dramatic, mysterious, places of no return, cosmic monsters lurking at the hearts of galaxies, yet also beautiful in their mathematical elegance, in the way they emerge inevitably from the equations of general relativity, in the roles they've played in shaping the universe we inhabit. As we lie here in the quiet darkness, contemplating these distant massive objects, there's something humbling and also strangely comforting about them, about their patient existence, their slow accumulation of matter over eons, their influence extending across galactic scales, shaping the environment around them without urgency or haste. They remind us that the universe operates on timescales vastly longer than human lives, that cosmic processes unfold over millions and billions and trillions of years, that there's a grandeur to existence that transcends our immediate concerns and daily struggles. In their silent darkness, in their invisible presence known only through their gravitational effects, in their patient waiting at the centers of galaxies, supermassive black holes embody something profound about the nature of the cosmos, about how structure emerges from simple laws acting over vast spans of time, about how the universe creates complexity and beauty from the interplay of fundamental forces. The magnetic fields around supermassive black holes deserve further contemplation, for they're integral to the entire system, threading through the accretion disk, anchoring the jets, organizing the plasma into coherent structures that persist for millions of years. These fields are generated by the motion of charged particles in the disk, amplified through dynamo processes, twisted and stretched by the differential rotation where inner regions orbit faster than outer ones, creating a complex, tangled topology that can store enormous amounts of energy. Sometimes this energy is released in sudden events, magnetic reconnection episodes where field lines break and reconnect in new configurations, accelerating particles and producing bursts of high-energy radiation, flares that can be detected across the electromagnetic spectrum from radio waves to gamma rays. Understanding these magnetic fields, their generation, evolution, and role in powering jets and producing radiation requires sophisticated computer simulations that solve the equations of magnetohydrodynamics in the extreme relativistic regime near the black hole. calculations that push the limits of even modern supercomputers and require careful testing against observations to ensure the simulations accurately capture the real physics of these systems. The photons that escape from near a supermassive black hole carry information about the environment they pass through, encoded in their energies, their polarization, their timing. By carefully analyzing this light, astronomers can reconstruct the conditions near the black hole, inferring the temperature and density of the accretion disk, the strength and geometry of magnetic fields, the velocity of orbiting gas. X-ray spectroscopy is particularly valuable, for the X-rays are produced in the innermost regions of the accretion disk, and their spectra show characteristic features produced by atoms like iron, lines that are broadened and distorted by the intense gravity, by the Doppler shifts from the rapidly orbiting gas, by the gravitational redshift as photons climb out of the deep gravitational well. These distorted spectral lines, carefully measured and modeled, provide some of our best evidence for the existence of event horizons and for the spin of supermassive black holes. For the details of the line shapes depend sensitively on how close the emitting gas is to the innermost stable orbit, which in turn depends on the black hole's rotation rate. Some supermassive black holes are found in binary systems, two black holes orbiting each other, though direct observations of such systems are challenging, because the black holes are so small compared to the distances involved. These binaries form when two galaxies merge, bringing their central black holes into proximity. And while the galaxies merge relatively quickly, over a few 100 million years, the black holes take much longer to actually merge, requiring some mechanism to shed angular momentum and bring them closer together. Initially, gravitational interactions with surrounding stars can do this, the black holes scattering stars and losing energy in the process. But at small separations, when the two black holes are separated by just fractions of a light year, there aren't enough stars in the vicinity to continue this process efficiently, and the binary can stall, the two black holes orbiting each other for billions of years without merging. This is called the final parsec problem, and various solutions have been proposed, including interactions with gas and circumbinary disks, or the possibility that three-body interactions with a third massive object could provide the final kick needed to bring the black holes together, or simply that given enough time, gravitational wave emission alone will eventually shrink the orbit, though this can take a very long time indeed at large separations. When supermassive black holes finally do merge, the event produces the strongest gravitational waves in the universe, ripples in spacetime carrying energies equivalent to a significant fraction of the black hole's total mass, radiated away in just a few minutes as the two objects spiral together and coalesce. These waves propagate outward at the speed of light, stretching and squeezing space perpendicular to their direction of travel, the amplitude decreasing with distance but remaining detectable across cosmological distances. For supermassive black hole mergers, the characteristic frequency of these waves is very low, ranging from nanohertz to millihertz depending on the masses involved, far too low to be detected by ground-based interferometers like LIGO, which are sensitive to frequencies of tens to thousands of hertz. Instead, detecting gravitational waves from supermassive black holes requires either pulsar timing arrays, which can detect nanohertz waves by monitoring the arrival times of pulses from millisecond pulsars over years or decades, or space-based interferometers like the planned LISA mission, which will be sensitive to millihertz waves by using laser links between spacecraft separated by millions of kilometers. The recent detection of a gravitational wave background by pulsar timing arrays suggests that there's a population of supermassive black hole binaries out there throughout the universe, slowly spiraling together, their waves overlapping to create a sort of gravitational hum that permeates all of space. This background is weak, detected only through careful statistical analysis of tiny correlated variations in pulsar timing across multiple pulsars, but its detection marks the beginning of a new era in gravitational wave astronomy, one that will allow us to probe the population of supermassive black holes in the universe, their merger rates, their masses, how they grow and evolve over cosmic time. Future observations, as more pulsars are added to timing arrays and as more years of data accumulate, will allow us to not just detect the background, but also resolve individual sources, picking out the loudest gravitational wave events from nearby merging supermassive black holes, measuring their properties with enough precision to identify the host galaxies, and perhaps even see electromagnetic counterparts, light produced as the black holes merge and disrupt their surrounding accretion disks. The electromagnetic counterparts to supermassive black hole mergers are uncertain, for unlike the mergers of stellar mass black holes, which can produce gamma-ray bursts in colonovae if their surrounding matter, supermassive black holes might not have sufficient gas in their immediate vicinity to produce bright electromagnetic signals. However, if the merging black holes are embedded in a circumbinary disk, or if the merger kicks up material from an accretion disk, there could be transient brightening, perhaps a flare in X-rays or optical light, perhaps changes in any existing jets, and astronomers are actively searching for such signals, monitoring known active galactic nuclei for periodic variations or sudden changes that might signal the presence of a binary system or a recent merger. The identification of electromagnetic counterparts to gravitational wave events from supermassive black holes would be enormously valuable, allowing us to pinpoint the host galaxy, to measure the redshift and therefore the distance, to study the environment and understand the astrophysical context of the merger, information that gravitational waves alone cannot provide. Consider for a moment the journey of a photon born in the accretion disk of a supermassive black hole in a distant galaxy, emerging from plasma heated to millions of degrees by friction and compression, carrying energy away from that extreme environment, beginning a journey across space that will take millions or billions of years. This photon, a quantum of electromagnetic energy, travels through the disk, perhaps being scattered by electrons, perhaps being absorbed and re-emitted many times before finally escaping into space, and then it travels outward through the galaxy, through intergalactic space, across the expanding universe, its wavelength being stretched by the expansion, redshifted to longer wavelengths, perhaps starting as an X-ray and arriving at Earth as visible light or even infrared, depending on the distance traveled. Along the way, it might pass through clouds of gas, gravitational fields of galaxies, and clusters that bend its path slightly, magnetic fields that rotate its polarization, but it continues, persistent, traveling in a straight line through space-time, following a geodesic, the natural path determined by the curvature of space around it, until finally, after crossing perhaps most of the observable universe, it enters the aperture of a telescope on Earth, focused onto a detector where it deposits its energy, triggering a cascade of electrons in a CCD chip recorded as a single count in a data file, one photon among trillions captured during an observation, yet each carrying information, each telling part of the story of its origin and its journey. From the patterns in these photons, from the spectrum and timing and polarization and spatial distribution, astronomers reconstruct the properties of distant supermassive black holes, inferring masses and spins and accretion rates, measuring distances and redshifts, building up a census of these objects across cosmic time. It's a remarkable process, extracting so much information from such faint signals, and it requires sophisticated instruments, carefully calibrated, operated with precision, their data analyzed with complex algorithms and models that account for all the effects the light has experienced on its journey. And yet it works. The observations match the predictions of theory. The inferred properties make sense in the context of what we know about galaxy evolution and cosmology. The pieces fit together into a coherent picture that has been refined and tested over decades of observations, a testament to the power of the scientific method and to human ingenuity in devising ways to study objects so distant and extreme. The sound of a supermassive black hole, if such a thing could be said to exist, would be impossibly deep, a rumble at frequencies far below the range of human hearing, for when supermassive black holes orbit each other in binary systems, they produce gravitational waves with frequencies corresponding to their orbital period, typically years or decades, translating to nanohertz or even picohertz frequencies, billions of times lower than the deepest sound a human can hear. But if we could somehow speed up time, compressing millions of years into seconds, we might hear a low drone slowly rising in pitch as the black holes spiral closer together, getting louder as the orbital frequency increases, faster and faster, louder and louder, culminating in a final chirp as they merge, a signature sound that gravitational wave astronomers listen for in their data, represented not as actual sound waves, but as fluctuations in space-time that are converted to audio frequencies for analysis and presentation. These chirps, when detected, are remarkably pure, clean signals that match the predictions of general relativity with stunning precision, confirming not just that black holes exist and merge, but that Einstein's century-old theory accurately describes gravity even in these most extreme conditions. The interior geometry of a rotating black hole is even stranger than that of a non-rotating one, for the rotation creates not just the ergosphere, but also potentially multiple event horizons, an outer one and an inner one, with a region between them where particles could, in principle, orbit in the opposite direction to the black hole's rotation. Though getting into this region would require passing through the outer event horizon, and escaping would require passing through the inner one, both of which are one-way boundaries. So in practice, this interior region is just as inaccessible as the singularity itself. The singularity in a rotating black hole is also different from the point singularity of a non-rotating one, predicted to be a ring rather than a point, a circle of infinite density located in the equatorial plane of the black hole, though again these predictions come from classical general relativity and likely break down when quantum effects are included. The ring singularity has some curious properties, at least in the classical theory, including the possibility that passing through it might lead not to destruction, but to another region of spacetime, perhaps another universe or another part of our own universe, ideas that have inspired much speculation but remain purely theoretical, for we have no way to test them and likely never will, given that any such journey would require crossing an event horizon first, permanently cutting off the traveler from our observable universe. Supermassive black holes, for all their strangeness and mystery, are in some ways simpler than other astrophysical objects, for they're characterized by just a few parameters: mass, spin, and potentially electric charge, though the latter is thought to be negligible in practice, since any significant charge would quickly be neutralized by attracting opposite charges from the surrounding plasma. This simplicity, encoded in what's called the no-hair theorem, states that black holes have no other properties, no additional features or structure, regardless of what fell into them, all the complexities of the infouling matter being erased, leaving only these three numbers to describe the black hole completely. This is quite different from, say, stars, which have complex internal structure, composition gradients, convection zones, magnetic fields, surface features, and many other properties that vary from star to star. Black holes, by contrast, are described by their position in a three-dimensional parameter, space, of mass, spin, and charge, and any two black holes with the same values of these parameters are completely indistinguishable, identical in every respect, at least according to classical general relativity. This simplicity is both elegant and profound, suggesting that black holes are in some sense fundamental objects in nature, the ultimate end state of gravitational collapse, stripped of all unnecessary details, reduced to their essential gravitational essence. Of course, the environment around black holes is anything but simple, with accretion disks, jets, magnetic fields, orbiting stars, all the rich phenomenology that we observe. But these are features of the surroundings, not of the black hole itself, which remains aloof, defined only by its mass and spin, its event horizon a perfect mathematical surface, a boundary in spacetime that admits no structure or variation. This distinction between the black hole proper and its environment is important conceptually, helping us separate what's fundamental about black holes from what's circumstantial, what depends on the particulars of how they formed and what's around them. And it allows for precise calculations and predictions, for general relativity tells us exactly what the spacetime geometry around a black hole should be given its mass and spin, and observations can test these predictions, comparing the measured properties of, say, gravitational waves or X-ray spectra with theoretical expectations, checking whether nature actually conforms to the elegant simplicity that the no-hair theorem suggests. There have been suggestions that quantum effects might add additional features to black holes, giving them hair after all in some subtle quantum sense, with information about infalling matter being encoded in quantum correlations between the interior and exterior or in subtle perturbations to the Hawking radiation. But these ideas are speculative and difficult to test, requiring a complete theory of quantum gravity to make definite predictions. For now, the no-hair theorem remains a guiding principle, a simplification that seems to hold in the classical regime and that makes the mathematics of black holes tractable, allowing us to calculate their properties and compare with observations. Whether this simplicity survives when quantum mechanics is fully incorporated remains an open question, one that will require both theoretical insights and potentially new observations to resolve, perhaps of primordial black holes or the final stages of black hole evaporation where quantum effects become dominant. The cosmic web, that vast network of filaments and voids that defines the large-scale structure of the universe, is intimately connected to the distribution of supermassive black holes, for black holes form at the centers of galaxies, and galaxies trace out the cosmic web, clustering along filaments and at their intersections, avoiding the great voids that occupy most of space. The formation of this structure began in the early universe, with tiny quantum fluctuations in density during inflation, blown up to cosmic scales, seeding the growth of structure through gravitational instability, dark matter collapsing into halos, ordinary matter following, gas cooling and fragmenting to form stars and galaxies, and at the centers of the largest halos, supermassive black holes growing alongside the galaxies themselves. The cosmic web we see today, observed through galaxy surveys that map the three-dimensional distribution of millions of galaxies, is the result of nearly 14 billion years of this growth, driven by gravity, shaped by the expansion of the universe, influenced by dark energy that has accelerated that expansion over the past few billion years, creating a dynamical, evolving structure that will continue to change over future eons. Supermassive black holes trace this structure, their population reflecting the underlying distribution of dark matter and the history of galaxy assembly. The most massive black holes are found in the most massive galaxies at the centers of rich clusters, where many galaxies have merged together over billions of years, their central black holes coalescing to form single giant black holes weighing tens of billions of solar masses. Less massive black holes are found in smaller galaxies in less dense environments, in the field and in small groups, reflecting the slower assembly history of these systems. By studying the demographics of supermassive black holes, their mass function, how many there are at each mass range, how this distribution changes with cosmic time, astronomers can learn about the processes that govern galaxy assembly, about the rates of mergers and accretion, about how feedback from active black holes regulates star formation, all encoded in the statistical properties of the black hole population. The sound of a pulsar, that rhythmic tick-tick-tick of radio pulses arriving at Earth with stunning regularity, is one of the tools astronomers use to detect gravitational waves from supermassive black holes. Pulsars are neutron stars, the collapsed cores of massive stars that have exploded as supernovae, spinning rapidly, some rotating hundreds of times per second with intense magnetic fields, channeling radiation into narrow beams that sweep across space like cosmic lighthouses. When a beam sweeps across Earth, we detect a pulse, and by timing these pulses over months and years, astronomers can measure the rotation of the pulsar with extraordinary precision, better than the best atomic clocks. But gravitational waves passing through the space between the pulsar and Earth change the distances slightly, stretching and compressing space, causing the pulses to arrive slightly early or late in a characteristic pattern. And by monitoring many pulsars across the sky and looking for correlated changes in their pulse arrival times, astronomers can detect these subtle effects of gravitational waves, waves with wavelengths of light years, periods of years, produced by supermassive black hole binaries across the universe. It's an ingenious technique, using the galaxy itself as a gravitational wave detector, with pulsars serving as the test masses and Earth as the detector station, sensitive to waves at frequencies completely inaccessible to ground-based or even space-based interferometers. The future holds many possibilities for advancing our understanding of supermassive black holes. New telescopes, both on the ground and in space, will provide ever-sharper views of the regions around black holes, resolving smaller structures, capturing dynamics on shorter timescales, measuring properties with greater precision. The Event Horizon Telescope continues to expand, adding more stations, observing at shorter wavelengths where resolution is even better, capturing movies rather than static images, showing how the accretion flow changes over time. Space missions like LISA will open the millihertz gravitational wave window, detecting thousands of supermassive black hole mergers, tracking them as they spiral together over months or years, providing precise measurements of masses and spins, possibly detecting gravitational wave memory effects and other subtle phenomena predicted by general relativity, but not yet observed. Pulsar timing arrays are being expanded with more pulsars monitored at higher cadence, improving sensitivity to nanohertz gravitational waves, aiming to detect individual loud merger events within the next decade. And new theoretical insights driven by improved simulations and possibly by breakthroughs in quantum gravity will deepen our understanding of what black holes are, how they form and evolve, what happens inside them, how they fit into the larger story of cosmic structure formation. There's also growing interest in intermediate mass black holes, objects weighing hundreds to hundreds of thousands of solar masses, potentially bridging the gap between stellar mass and supermassive black holes, possibly representing an evolutionary link or an alternative formation pathway. Evidence for these objects is tentative, coming from observations of ultraluminous X-ray sources in nearby galaxies, from gravitational wave detections of unusually massive merging black holes, from subtle dynamical signatures in dense star clusters, but confirming their existence and understanding their role in cosmic evolution remains a challenge. If intermediate mass black holes are common, they might seed the formation of supermassive ones, merging together or accreting gas to grow to larger masses over cosmic time, and understanding this population could resolve some of the puzzles about how supermassive black holes grew so large so early in the universe's history. As we drift deeper into relaxation, into that space between waking and sleeping, we can imagine ourselves floating in the vastness of space, far from Earth, far from the Sun, far even from our galaxy, out in the intergalactic void where distances are measured in millions of light years, and the nearest galaxy is just a faint smudge of light against the darkness. From here, we can look back at the Milky Way, seeing it face on, perhaps, a spiral of stars and gas spread across 100,000 light years, and somewhere near the center, invisible at this distance but known to be there, is Sagittarius A star, that supermassive black hole around which 400 billion stars orbit in their slow, graceful dance. We can imagine zooming in, moving closer, the galactic center growing brighter as we approach, stars becoming individually visible, their density increasing, tens of thousands of stars packed into every cubic light year near the center. And there, at the very heart of it all, a region of darkness, no stars, just the subtle gravitational perturbations that reveal the presence of the black hole, pulling on everything around it, anchoring the galaxy, silent and patient and immensely powerful. We could continue inward, approaching the event horizon, watching as stars near the black hole move faster and faster in their orbits, some taking just years or even months to complete one circuit around this invisible anchor, moving at thousands of kilometers per second, relativistic speeds, where time dilation becomes significant, where the star's light is Doppler shifted noticeably, blue when approaching, red when receding, where gravitational lensing bends the light from background stars, creating multiple images, arcs and Einstein rings, visual distortions that are subtle at large distances but dramatic close to the event horizon. Closer still, if there's an accretion disk, we'd see its glow, hot plasma spiraling inward, glowing in X-rays and ultraviolet, perhaps with jets emerging perpendicular to the disk. Streams of particles accelerated to nearly light speed, extending outward for thousands or millions of light years, invisible in optical light but brilliant in radio waves, structures so large they dwarf the galaxy itself, all powered by matter falling into that central darkness, converting gravitational potential energy to kinetic energy, to thermal energy, to radiation with an efficiency that exceeds fusion, the process that powers stars. And finally, at the event horizon itself, we'd see the ultimate boundary, not as a physical surface, but as a place where light rays bend back on themselves, where the escape velocity equals the speed of light, where space-time curvature becomes so extreme that all futures point inward, toward the singularity, where time and space exchange roles in a sense, where causality takes on strange properties, where every world line, every possible trajectory through space-time leads inexorably to the same endpoint at the center, in finite proper time for anyone making the journey, in infinite coordinate time for anyone watching from outside, asymptotically frozen at the horizon, never quite crossing from the external perspective, yet definitely crossing and continuing to fall from the infalling perspective, a duality that arises from the choice of reference frame, from the way we parameterize time, from the relativity of simultaneity that underlies all of special and general relativity. The mathematics of black holes is beautiful, elegant, expressed in the language of differential geometry, of tensor calculus, of geodesics and curvature tensors, the Einstein field equations relating the geometry of spacetime to the distribution of energy and momentum, a set of 10 coupled nonlinear partial differential equations whose solutions describe how matter curves spacetime and how that curvature affects the motion of matter. For black holes, the solutions are particularly elegant, the Schwarzschild metric for non-rotating black holes, the Kerr metric for rotating ones. Exact solutions that can be written down explicitly, studied analytically, understood in detail, unlike most solutions in general relativity which require numerical approximation. These solutions reveal the structure of spacetime around black holes, the locations of horizons and singularities, the behavior of light and particles, the stability of orbits, all following mathematically from the field equations and the requirement that the solution represent a black hole of given mass and spin. The elegance of these solutions, their mathematical beauty, is part of what makes black holes so fascinating to physicists, for they're not just astrophysical objects, but also elegant mathematical structures, solutions to Einstein's equations that exhibit remarkable properties and symmetries. Time passes differently near black holes, and in contemplating this, we touch on one of the deepest insights of relativity. That time is not absolute but relative, flowing at different rates for observers in different gravitational fields or moving at different velocities. Near a supermassive black hole, this effect can be dramatic. Someone hovering just outside the event horizon, experiencing time at a much slower rate than someone far away. A minute for them corresponding to hours or days or longer for the distant observer, the exact factor depending on how close to the horizon they are. This time, dilation is a real physical effect, not just an artifact of perception or measurement. Clocks literally run at different rates, processes occur at different speeds, aging happens more slowly near massive objects than far from them. Astronauts on the International Space Station age slightly slower than people on Earth's surface by a few microseconds per year, a tiny effect that has been measured and confirmed. Near a supermassive black hole, the effect would be millions of times larger, profound enough to allow time travel into the future, in a sense, for someone who could somehow survive hovering near the event horizon for a subjectively short time, and then escape would emerge to find that far more time had passed in the outside universe, years or centuries or millennia, depending on how close they were and how long they stayed. This isn't time travel in the science fiction sense of moving backward in time, which general relativity generally forbids through the protection of causality, but it's a genuine asymmetry in the flow of time, a consequence of the way gravity curves not just space, but space-time together. The stars that orbit closest to supermassive black holes are subject to extreme tidal forces, the difference in gravitational pull between their near and far sides being substantial, potentially stretching them, distorting them from their normal spherical shapes into elongated ellipsoids. Though for supermassive black holes, these tidal forces are actually weaker than for stellar mass black holes at the event horizon, a consequence of the larger size of the event horizon, for tidal forces decrease as black hole mass increases, being inversely proportional to the square of the black hole's mass. This might seem counterintuitive, that larger black holes have weaker tidal forces at their event horizons, but it's a consequence of the fact that the event horizon radius grows linearly with mass, while tidal forces depend on the gradient of the gravitational field, which falls off faster for larger black holes. This means that for supermassive black holes, particularly the most massive ones weighing billions of suns, you could cross the event horizon without immediately being torn apart, surviving for some time as you fell toward the singularity before tidal forces grew large enough to be fatal, whereas for a stellar mass black hole, the tidal forces at the event horizon would be instantly catastrophic, pulling apart any macroscopic object that tried to cross. Occasionally, a star does pass close enough to a supermassive black hole to be disrupted by tidal forces, an event called a tidal disruption event, where the star is stretched and torn apart, some of its material falling into the black hole while the rest is ejected at high velocities, creating a bright transient that can be detected across cosmological distances. These events produce characteristic light curves, brightening rapidly as the stellar material falls into the black hole and forms a temporary accretion disk, then fading over months or years as the material is consumed or dispersed. Astronomers have detected dozens of these events, studying them to learn about the properties of both the stars and the black holes involved, using them to find and characterize supermassive black holes that are otherwise dormant and difficult to detect. The rate at which tidal disruption events occur depends on the stellar density near the black hole, typically one event every 10,000 to 100,000 years per galaxy, rare enough that seeing one requires monitoring thousands of galaxies, but common enough that with modern surveys that observe millions of galaxies, several are detected each year, providing a steady stream of new events to study and analyze. The concept of a photon sphere around black holes is another fascinating consequence of the extreme curvature of spacetime. This is a spherical surface at 1.5 times the Schwarzschild radius, about 1.5 times the radius of the event horizon for a non-rotating black hole, where light can orbit the black hole in circular paths, neither falling in nor escaping, but endlessly circling, at least in principle, though these orbits are unstable, meaning that any slight perturbation will cause the photon to either spiral inward and cross the event horizon or escape to infinity. The photon sphere is important for understanding the appearance of black holes, for it determines where light rays that pass near the black hole will be bent enough to circle around and possibly form multiple images of background sources, creating the complex light patterns we see in simulated images of black holes, including the bright ring in the Event Horizon Telescope images, which is produced by photons from the accretion disk that orbit multiple times around the black hole before escaping to reach our telescopes, amplified and focused by the gravitational lensing effect. In rotating black holes, the photon sphere splits into different surfaces depending on whether light is orbiting with or against the black hole's rotation, prograde versus retrograde orbits having different radii, and between the two photon surfaces lies the ergosphere, that region where spacetime is dragged along with the black hole's rotation, where nothing can remain stationary with respect to distant observers, everything forced to rotate in the same direction as the black hole, though still possible to escape, unlike from within the event horizon. The existence of the ergosphere allows for the Penrose process, a theoretical mechanism by which energy can be extracted from a rotating black hole, where a particle entering the ergosphere splits into two, one falling into the black hole, the other escaping with more energy than the original particle had, the energy coming from the black hole's rotational energy, potentially allowing a very advanced civilization to tap black holes as power sources, extracting their spin energy over time, gradually slowing their rotation. This process might occur naturally through interactions with accretion disks and magnetic fields, potentially regulating black hole spin and preventing them from spinning up to the theoretical maximum rate. The study of black holes intersects with fundamental questions about the nature of reality, about what exists and what can be known, about the limits of observation and measurement, about the relationship between mathematics and physical reality. Black holes are real objects, observed indirectly but conclusively, yet they contain within them regions that are fundamentally unobservable from our universe, hidden behind event horizons, their interiors forever sealed off from external investigation. This raises philosophical questions about the nature of existence, whether something that cannot be observed in principle can still be said to exist, whether the unobservable interior of a black hole is part of our universe or separate from it, whether the information that falls into black holes is lost or preserved in some subtle way. These are not just abstract philosophical puzzles, but questions with potential implications for physics, for quantum mechanics teaches us that information is fundamental, cannot be destroyed, yet black holes seem to violate this principle, at least superficially. And resolving this apparent contradiction, the black hole information paradox may require new physics, new understanding of how quantum mechanics and gravity fit together. The cosmic microwave background, that ancient light from the early universe, cooled and redshifted by cosmic expansion to microwave wavelengths, carries imprints of the conditions in the universe 400,000 years after the Big Bang, when atoms first formed and photons could travel freely through space without being scattered. These photons have been traveling for nearly 14 billion years, and along the way, some have passed near or through large structures, galaxy clusters with their deep gravitational potentials, and their paths have been affected, bent, and gravitationally lensed, their energies shifted by the motion of the structures they pass through, effects that are subtle but detectable through careful analysis. Supermassive black holes contribute to these effects only indirectly through the galaxies and clusters they inhabit, but they're part of the story, part of the web of matter and energy that has shaped the universe, and future observations of the cosmic microwave background with even greater sensitivity might detect the cumulative effects of all the structure in the universe, including the gravitational influence of supermassive black holes on the photons that stream past them on their journey from the surface of last scattering to our telescopes. As we near the deepest part of sleep, consciousness fading, awareness dissolving into dreams, we can carry with us the image of a black hole, not as a physical object, but as an idea, a region of space-time curved beyond everyday comprehension, a place where the laws of physics reach their limits, where time and space intertwine in ways that challenge our intuition, where matter and energy meet their ultimate fate, transformed and hidden, contributing to the mass and spin of the black hole, but losing all other identity, information erased or preserved in ways we don't yet understand. Mysteries that will occupy scientists for generations to come. Questions that may never be fully answered, but that inspire wonder and drive exploration, pushing us to develop new theories, new mathematics, new ways of thinking about the universe and our place in it. Supermassive black holes are anchors of galaxies, sculptors of structure, laboratories of extreme physics, cosmic mysteries resting in the centers of island universes, waiting patiently through the eons, silent testaments to the power of gravity and the strange beauty of the cosmos.